Hi everybody. This is a recording of my PhD defense presentation. Um, my name is Nikola Samardzic, and today I'll be defending my thesis on practical cryptographically private and verifiable computation through hardware-software co-design. Cryptography is already deployed everywhere. Internet traffic is encrypted and decrypted. We SSH onto our work machines. Digital certificates are used to authenticate websites we visit. We sign contracts online, and so on. Notice that all of these use cases provide guarantees about data. More recently, cryptographers have invented novel tools with impressive capabilities. These include private and verifiable computation. Now, these tools are fundamentally different because they provide guarantees about computation. Let's see more on that. So, what is private computation? Private computation refers to the ability to compute on data without revealing the data. And verifiable computation enables us to know that the correct computation was carried out and the correct result was produced. Let's focus on private computation first. Private computation enables a client to offload some compute onto a server without the client compromising the privacy of their data. Fully homomorphic encryption, or FHE, is a cryptographic tool that enables private computation on arbitrarily large programs without involving the client. Specifically, the client can encrypt their data, send it to the server computes on this encrypted data using FHE, and returns the encrypted result. Finally, the client decrypts the result. Because the data never leaves the client unencrypted, the client need not trust the server with their data. Let's motivate FHE by going through a more concrete use case. Our client is a pediatric surgeon that wants to classify a sensitive medical CAT scan using a deep neural network, or DNN. But performing a DNN inference would be too expensive on her hospital's local computer. Instead, she encrypts the CAT scan, and the DNN inference is actually run in the cloud on the encryption of the image. The neural network weights themselves can either be encrypted and hidden from the server or unencrypted. She receives her encrypted result back, decrypts it, and sees the diagnosis. As the DNN inference is run on encrypted data, the doctor does not need to trust the cloud provider to keep the CAT scan private. Now, the main drawback of FHE is that it is extremely slow, 4 to 5 orders of magnitude slower than unencrypted computation. For example, a ResNet 20 inference takes 20 milliseconds unencrypted, but 20 minutes when done on encrypted data. It's also very hard to use. Only FHE experts are able to write good FHE applications. While FHE allows the client to rest easy that their data is safe, it does not provide any guarantee that the server applied the correct function and returned the right result. This is where verifiable computation comes in. It allows the server to convince the client that the right computation was performed. SNARKs are the analog of FHE for verifiable computation. Similarly to FHE, SNARKs owe their popularity to their attractive cryptographic properties. Let's see how they work. So, aside from just computing the function f of x itself, the server will supply a small proof that convinces the client that the computation is carried out correctly. Given this proof, the client can check the correctness of arbitrarily complicated computations very cheaply. Going back to our example from earlier, let's look at how SNARKs could be useful for a doctor. Let's say that now, instead of being concerned with data privacy, the doctor does not trust that the server ran the correct neural network, or that the result that was returned is somehow incorrect. Using SNARKs, the server could prove that it applied the correct diagnostic software by attaching a small cryptographic proof that the doctor can use to cheaply verify that the result was produced correctly. There's an abundance of applications of FHE and SNARKs, many of which are already deployed. For FHE, these include private neural network inference and private information retrieval, while SNARKs have applications in low transaction cost blockchains, online auctions, and others. Governments and industry have already invested hundreds of millions of dollars to deploy FHE and SNARKs. Unfortunately, deploying this tech comes with significant hurdles, and the first is performance. So as I mentioned, FHE is 10,000 to 100,000 times slower than doing the same computation on unencrypted data. SNARK's performance issues are even more pronounced, up to 1,000,000 times slower than the same computation without verification. The second challenge is usability. FHE provides a restricted, low-level interface that prevents abstraction and composition, and both FHE and SNARKs come with unintuitive performance trade-offs. This is best illustrated by a paradigm of how a lot of FHE research was done in the past. FHE experts would port individual applications to FHE and publish papers about each application. These include ResNet, RNN, logistic regression, and others. Now, performance and usability challenges must be addressed to make private and verifiable computation pervasive. My thesis makes a significant leap towards addressing these challenges. So we bridge the gap between private and verifiable applications that users want at the top and transistors at the bottom. Specifically, we contribute two FHE hardware accelerators, F1 and Crater Lake, which close most of the performance gap between encrypted and unencrypted computation. We also contribute Bitpacker, a change to the state-of-the-art FHE implementation that improves performance on both accelerators and CPUs. We address the usability challenge by contributing Felipe, a compiler that exposes a simple, NumPy-style tensor programming interface for FHE. Felipe enables us to build a library that supports automatic translation of PyTorch models into FHE programs that do inference on these models. Finally, on the verifiable computation front, we contribute NoCap, a SNARK hardware accelerator. F1 and Crater Lake contribute 5,000x speedup over a CPU, while Bitpacker contributes an additional 60% gmean speedup. Felipe reduces the number of lines needed to code up an FHE program by gmean 25x, while meeting or exceeding the performance of manual baselines. And NoCap accelerates SNARKs by gmean 50x. This defense will focus on our FHE contributions. Now, I just want to quickly acknowledge that these papers are the work of many people and not just myself. I couldn't have done it without you guys. So here's the agenda for the rest of the talk. We just covered the intro, and I'll discuss some necessary background now. After that, we'll cover each contribution individually. FHE programs are static data flow graphs or circuits in the theoretical computer science sense. Each node of this circuit is a homomorphic operation or ciphertext. A homomorphic operation applied to a ciphertext acts on the underlying encrypted values. Since data is encrypted, data-dependent control flow is not possible. Now, circuits are not Turing complete, but sufficient for many applications, and these include machine learning. There are many different implementations of FHE called FHE schemes. They differ in their interface, that is, which data types and operations they support, as well as their implementation, that is, how ciphertexts look like and how homomorphic operations are applied. The two main types of FHE schemes are vector and scalar schemes. In vector schemes, each ciphertext encrypts a large vector of 16,000 to 64,000 elements. The vector elements can be integers or fixed point values. In contrast, ciphertext and scalar schemes encrypt only a single value. Vector schemes have larger ciphertexts, but much lower per element overheads compared to scalar schemes. This makes them ideal for data parallel computation, like machine learning and linear algebra. Most state-of-the-art FHE apps are implemented in vector schemes. My research and this defense focuses on vector schemes and the CKKS scheme in particular. While the data types that different vector schemes use are different, their actual implementation is pretty similar. So most of what you'll hear applies to all vector schemes. Okay, let's now go over FHE's interface and implementation in that order. A plaintext vector in FHE consists of tens of thousands of real numbers. We use a secret key to encrypt this plaintext into an FHE ciphertext. An FHE ciphertext is composed of two high-degree polynomials with large integer coefficients. So for example, 64k degree polynomials with 1600-bit coefficients. This implies a 25 megabyte ciphertext. Note that our focus is not improving the performance of this encryption process. So encrypting values into ciphertext is fast on pretty much any hardware. Instead, we're accelerating generic computation on FHE ciphertexts. FHE supports three operations on the underlying encrypted vectors. These are element-wise adds, element-wise multiplies, and cyclic vector rotates. Orange operands can also be plaintexts. Rotation amounts are always unencrypted. So this interface doesn't imply that a ciphertext multiplication can be implemented by simply multiplying the polynomials of the two ciphertexts. Let's see how the FHE interface is actually implemented. So to implement an FHE operation, we must actually perform many primitive polynomial operations. Specifically, FHE requires support for element-wise modular additions and multiplications, and two more complicated operations that have all-to-all dependencies. These are automorphisms, so structured permutations on polynomial coefficients, and number theoretic transforms, or NTTs, which are used to speed up polynomial multiplication. All FHE operations can be implemented using these four primitives. The illustration here shows the primitive operations we must apply to implement a ciphertext multiplication of ciphertexts x and y. To finish the operation, we must also key switch these results. Now, key switching is an FHE algorithm composed of hundreds and sometimes thousands of primitive operations. Thus, key switching is responsible for over 90% of compute in most FHE programs and is FHE's key kernel. We'll come back to it throughout this talk. Key switching also requires a large amount of auxiliary data in the form of key switch hints. Polynomial multiplication features prominently in FHE, and NTTs allow us to do these multiplications fast. If we want to multiply two polynomials, we need to convolve their coefficients. Naively, this involves multiplying each coefficient of one polynomial with each coefficient of the other. This takes n squared multiplies. However, by using the number theoretic transform, which is very similar to an FFT, except for modular arithmetic, we can reduce our number of multiplies to n log n. This is absolutely critical, as our polynomials often have 64,000 coefficients. To efficiently run FHE computations, we must use NTTs. Now let's zoom out a bit and talk about the broad structure of an FHE program. When we encrypt a ciphertext, it starts out with wide coefficients. As we compute deeper and deeper on ciphertext, the bit width of our coefficients shrinks through rescaling. This is necessary to keep precision in check. Eventually, the bit width becomes too narrow to support further computation. When we no longer have any bit width to proceed, it seems like we're stuck. We can't perform any more computation without making our values undecryptable. Fortunately, FHE has a trick up its sleeve. We can apply an expensive procedure called bootstrapping, which allows us to refresh our ciphertext back to its original bit width. An important implication of all this is that it is necessary for us to be able to compute on polynomials that have varying coefficient bit widths. To support both very large and varying coefficient bit widths used in FHE, we employ the residue number system, or RNS, to implement modular arithmetic. RNS leverages the Chinese remainder theorem to represent an integer modulo a large modulus as many smaller integers modulo the prime factors of the large modulus. These small integers are called residues. So here's an example. The integer 123 modulo 3 times 7 times 13 can be represented in RNS form as 123 modulo 3, which is 0, 123 modulo 7, which is 4, 123 modulo 13, which is 6. The magic of RNS is that now a multiplication of two 1600-bit coefficients can be implemented as an element-wise multiplication of the residues. And addition works the same way. Because multiplier complexity scales roughly quadratically in bit width, Arithmetic is significantly cheaper in RNS than operating on large integers directly. This idea also works for polynomials. So a polynomial with 1600-bit coefficients can be decomposed into many residue polynomials, each with word-size coefficients. Polynomial multiplication can then be applied per residue polynomial pair. Let's tie all these concepts together by looking at FHE's stack. At the top here, we have FHE applications. All these are implemented in terms of the three operations that FHE supports. These are adds, multiplies, and rotates. All FHE ops, in turn, are implemented in terms of the four primitive polynomial operations. Bootstrapping is just a very special kind of FHE application, used by most other FHE apps. You can think of it as a core library function for FHE, but it is also implemented just in terms of the three FHE ops. Key switching is an important algorithm, but it is not exposed to FHE apps. It's implemented using the four primitive polynomial operations. Let's wrap up the background by going over the architectural implications of what we discussed. First, FHE isn't a single application. We're not accelerating encryption or decryption. We're accelerating the computation on encrypted data. These computations are general purpose, and we want to accelerate all of them. While these computations are quite diverse, they all rely on the four primitive polynomial operations we discussed. It's important to accelerate the primitive operations in a composable way. Third, our operands are very large. Ciphertext can take up several megabytes, and key switch hints, which we briefly saw earlier, can take tens of megabytes. Data movement is absolutely key. Finally, our data flow is completely static. Data-dependent branches are not possible in FHE, allowing us to know all control flow ahead of time. Jumping into F1, here are the principal differences between it and prior work on FHE accelerators. We target ASICs instead of FPGAs, forcing us to reckon with larger data movement problems. We accelerate entire FHE programs instead of only specific kernels. Finally, we accelerate primitive operations instead of building over-specialized pipelines. And here is F1's architecture. F1 supports wide vector functional units tailored to FHE, including novel functional units for automorphisms and entities. Functional units and register files are grouped into 16 compute clusters. F1 includes an explicitly managed memory hierarchy with a highly banked scratchpad. A high bandwidth on-chip network is used to connect the scratchpad and compute clusters. Instructions are scheduled statically with distributed control flow. We'll now start to discuss some interesting features of F1's design. We designed and implemented a complete software stack that compiles FHE programs expressed in a simple domain-specific language to scheduled F1 instructions. An FHE program written in our DSL precisely describes the data flow graph. Using the fact that we know all data dependencies ahead of time, we can schedule each instruction at a precise cycle. We can also manage our memory hierarchy statically, making sure the data is efficiently fetched ahead of time and replaced using a close approximation of the optimal Belides min algorithm. Each of F1's compute clusters is built out of four basic functional units that process vectors of configurable length n using a fixed number of lanes e, equal to 128 in our implementation. Vectors have 32-bit elements, and we leverage RNS to avoid wide and variable width arithmetic. All functional units are fully pipelined and process e elements per cycle. This is easy for element-wise adds and multiplies, but pretty challenging for automorphisms and entities. I'll illustrate the challenge in implementing the automorphism and entity units using a toy 16-coefficient polynomial. As we saw, F1 processes coefficients, e equals 128 elements at a time. Thus, we say that in F1, a 16,000 element vector is divided into 128 chunks, with each chunk having 128 coefficients. The slide here illustrates dividing the 16 coefficient polynomial into 4 chunks, each holding 4 coefficients. The vector add and multiply units are easy to implement with this data path because they operate coefficient-wise on the residue polynomials. This means we can process data independently, chunk by chunk. In contrast, implementing the NTT on automorphism units is hard. Each coefficient of the output may depend on any of the input coefficients. As coefficients of the input polynomial may be distributed across up to 128 chunks, creating a pipeline data path that produces these outputs is non-trivial. Let's see how we did this for automorphisms. Automorphisms are a very general concept from abstract algebra, but in the context of FHE, automorphisms are used to implement rotations of encrypted values. So here we see the data flow for implementing a ciphertext rotation. In the context of FHE, automorphisms are roughly just very specific permutations of coefficients. So to implement the cyclic rotation by k elements, we use the permutation that moves the ith coefficient to the coefficient 5 to the k times I mod n, where n is the polynomial degree. So here's an example automorphism applied to our toy 16 coefficient polynomial. Different colors here represent different chunks of the input polynomial. This example demonstrates that automorphisms permute coefficients across chunks, making them hard to pipeline. Now, we're the first to notice that an automorphism can be decomposed into a fully pipelined functional unit. The unit divides the automorphism into a pipeline of fixed permutations that operate only within chunks and not across chunks. To accomplish this, we first apply a set of permutations to each chunk, then transpose, then apply a different set of permutations, and finally transpose back. Again, this decomposition allows us to completely avoid permutations across chunks. Since all permutations are applied locally within chunks, they're cheap to implement and pipeline. At the core of the pipeline is a novel SRAM-based fully pipelined matrix transpose subunit. This subunit is also critical in the design of the NTT unit. Here's the area and thermal design power, or TDP breakdown for F1. The chip has an area of 151 millimeters squared and consumes a maximum of 180 watts. We measure F1's performance on a diverse set of benchmarks, including neural network inference, logistic regression training, database lookup, and single slot bootstrapping. The bootstrapping here is called single slot because it is only able to bootstrap a single value at a time. This means that a ciphertext with 16,000 elements would require 16,000 of these single slot bootstraps. Fully packed bootstrapping bootstraps all ciphertext slots at once, but F1 does not support this well. We'll see why later. So here's the speedup versus state-of-the-art on the LoLa neural networks, logistic regression, database lookup, and single slot bootstrapping. This means F1 boasts a G-mean speedup of 5400x over state-of-the-art. This plot shows that F1 achieves high resource utilization over time. In summary, F1 demonstrates a G-mean 5400x speedup over state-of-the-art. And notably, it does this without sacrificing programmability, because its ISA is at the level of primitive polynomial operations. To motivate Crater Lake, our second FHE accelerator, let's talk about challenges specific to large FHE programs. The bottom line is that large FHE programs require ciphertexts that are up to 10x larger than what F1 supports well. Let's see why. So as we mentioned, ciphertexts start out with large coefficient bit widths that are slowly narrowed during computation. Fully packed bootstrapping refreshes all elements in the ciphertext back up to a larger size, thus enabling more computation. This means FHE can support arbitrarily deep computation by separating the program into regions of limited depth and bootstrapping in between. But as the slide shows, fully packed bootstrapping requires working with large ciphertexts, which F1 does not effectively support. This is why we only saw single-slot bootstrapping results for F1. Therefore, F1 supports well only those programs that are shallow enough to not require bootstrapping. Note that the y-axis here shows the footprint of a single ciphertext, and getting good operand reuse may require storing many of them on chip. By supporting sufficiently large ciphertexts, Crater Lake enables acceleration of arbitrarily deep FHE programs. Targeting these large ciphertexts requires new architectural and algorithmic techniques. By adopting the latest FHE algorithms, the Crater Lake architecture scales to larger ciphertext and die areas than F1. It sports a new logical organization with an extremely wide 2048-lane vector uniprocessor. It has only a single level, very large, explicitly managed register file and new functional units that are tailored for key switching. This logical organization was made possible by a novel physical organization. The lanes of the processor are distributed across 8 lane groups and connected by a fixed function network. The insight behind this network is the key to enabling Crater Lake's uniprocessor architecture. The network only supports transposes of elements across vector lanes. This simplicity allows it to have an order of magnitude higher throughput than the network in F1. And that in turn allows us to scale Crater Lake to a very large die size. To make all this work, we also need to contribute a new tiling of FHE ciphertexts across the chip. Let's look at the system configuration and results. The table here shows Crater Lake's area and the breakdown by component. Overall, our Crater Lake configuration requires 472 millimeters squared, a lot bigger than F1. We compare Crater Lake to baselines with similar area and power budgets, a 32-core server CPU, as well as F1 Plus, a scaled-up version of F1. The table here reports the performance of Crater Lake on deep and shallow benchmarks measured in milliseconds. Crater Lake achieves very large speedups over the CPU implementation, ranging from 2900 to 8600x. Speedups are similar across deep and shallow benchmarks, showing that Crater Lake provides robust gains across FHE program types. We also compare Crater Lake to F1 Plus, a scaled-up version of F1. Crater Lake achieves large speedups over F1 Plus on deep benchmarks, outperforming it by 11x and up to 18x. By contrast, Crater Lake and F1 Plus achieve comparable speeds on small benchmarks, with a G-mean speedup of only 30%. These stark differences demonstrate that prior FHE accelerators are efficient only on shallow computations and falter on deeper ones. The per-benchmark power breakdowns show that Crater Lake uses most of its energy on compute, despite FHE's data movement challenges. This indicates that FHE is a great target for hardware specialization, and that outperforming Crater Lake without fundamental cryptographic and algorithmic advances would be hard. Crater Lake also achieves high utilization across benchmarks. In summary, by identifying a novel way to lay out compute and data, Crater Lake is able to scale the large ciphertext necessary to support all FHE programs, regardless of their depth. Now let's see a bit of Bitpacker. Okay, so CKKS is the state-of-the-art FHE scheme. Its most performant implementation is RNS-CKKS, which implements all FHE primitives in the residue number system, or RNS. This implementation is used in F1, Crater Lake, and most other FHE accelerators. The problem with RNS-CKKS is that the precision of operations, hardware word size, and performance are all tightly coupled. So let's illustrate this with an example. Say we have a 64-bit word size accelerator, and say that we have an application that requires 20 bits of fixed point precision. In RNS-CKKS, we want the residues to be roughly 20 bits wider than the precision we are targeting. Thus, we'll have 40-bit residues. The issue here is that we're only using 40 out of 64 bits of the accelerator. Not ideal. We see the portion of the data path that's not used in red. This is especially bad when we remember that Crater Lake's performance is bound by the power of its multipliers. Now, each application will have its own optimal precision, right? Even more painfully, different precisions are often used within a single application. This means that any accelerator, regardless of its chosen bit width, will be underutilized for most applications. This problem was acknowledged and partially remedied by prior work. Sharp shows that some applications can be tuned so that they have both good performance and precision using a 36-bit hardware word size. But this tuning is application specific and doesn't always work. Bitpacker addresses the root of the problem. It completely removes the coupling in RNS-CKKS. You just use the residues that match the word size, with the exception of the last one or two residues, shown in blue in the slide. So this makes narrow word sizes optimal, both for performance and for precision. And it allows a narrow bitwidth accelerator to support any precision without bits of the data path going unused. This results in a 59% G-mean speedup over RNS-CKKS. Now let's tackle the challenge of FHE usability. So writing FHE programs is hard. FHE does not present a programming model similar to the one that we're used to. Instead of working on individual scalars, it works on long encrypted vectors and does not provide random access to the elements of these vectors. This makes compiling programs to FHE quite a challenging task. Existing compilers address small parts of this puzzle and get limited speedups. Even doing this manually is tricky. In our research, we found that the leading logistic regression FHE implementation has a 10x performance bug. Felipe compiles all programs we've encountered, no matter how large, and exposes an expressive NumPy-style tensor interface. This interface leads to a 25x G-mean reduction in lines of code compared to manual implementations. Felipe automatically chooses the right way to map data onto ciphertext vectors and manually places bootstraps. All this while matching or exceeding the performance of state-of-the-art manual baselines. Let's see how. FHE's interface is very restrictive. The only operations FHE supports are element-wise multiplies, element-wise adds, and cyclic vector rotates. But we want to use FHE to do complicated things like DNN inference. Seems like a bit of a pain to implement something like a convolution in this interface. Well, it's worse than you think. So vectors encrypted under an FHE ciphertext are very large. 32,000 elements is standard. On the one hand, reordering elements encrypted in a vector is very expensive. It requires a lot of rotations and multiplications. On the other hand, to get good use out of FHE operations, we actually must pack the ciphertext with as much data as possible. And since applications rarely use vectors this large, we must pack higher dimensional blobs of data onto a single ciphertext. So for example, an entire matrix or even tensor. But how do we do this packing without having to frequently reorder elements within a ciphertext? Before Felipe, this was done manually by FHE experts. To see how hard doing this manually is, let's use an example. So let's try to do a bunch of matrix vector multiplies of a 4x4 matrix A and a 4-element vector X. So we want to compute AX, A squared X, A cubed X, and so on. Assume that a ciphertext holds 16 elements and that both A and X are encrypted. I mean, how hard can it be? Okay, so we said we want to pack data as much as possible. So okay, let's cram the entire matrix A into one ciphertext, and let's do it in row major order. And let's say that we put the vector in consecutive slots of the ciphertext like so. So can we compute all the partial products in one FHE multiply? Let's give it a shot. So to do that, we first replicate the vector X into the remaining slots. So this is done by rotating and accumulating. So as you can see, first we rotate by 4 and add, and then we take that and rotate by 8 and add back. Okay, now we can do the multiplication of all and computation of all the partial products in one FHE multiply. And then we have to sum all these partial products to get the result. So this is similar to how we did a replication, but kind of in reverse. The add symbols here indicate garbage partial sums. Okay, and now we want to do this multiple times, right? We want a squared x, a cubed x, and so on. Can we just repeat the same steps from the beginning? Well, no, right? The issue here is that the output data layout doesn't really match what we had at the beginning. So we can't just apply the same steps blindly. Okay, oh well, we can add some ops to adjust the layout back to what it was at the beginning. So we mask the garbage out, do more rotates and adds, and one final mask to get the result in the right layout. Okay, so this will work, but we're not super happy with all this overhead. Note that the overhead is even worse with larger ciphertexts and matrices. Even if we adjust layouts optimally with the 128 by 128 matrix and 16K element ciphertext, we'll actually have a 10x performance overhead just from adjusting the layouts. So is there any way to do better? So there is a better way. What we can do is in the second matrix multiplication with A, we can actually use a different layout than in the first. So we again replicate, but a bit differently than before, as you can see. We multiply by A and accumulate partial products. And again, this is a little different than before, but same principle. And look, it seems like we got lucky, right? So the layout at the end of the second multiplication actually matches that at the start of the first multiplication. So for the next multiplication, we can apply the same procedure we used the first time around, right? So we're happy with this, but let me ask you a follow-up question. Will this work for 5 by 5 matrices? Well, not at all, right? The matrix doesn't even fit into a single ciphertext anymore. So how can we do better? Is there a nicer interface we can expose? So here's our answer. So Felipe exposes a more expressive tensor interface and allows users to think at the level of tensors and tensor operations instead of ciphertexts, FHE operations, and layouts. We first replicate the vector along a new dimension. We then do the element-wise multiplication with the matrix A and return the sums along the dimensions we created earlier. To do multiple matrix vector multiplications, we just call the function many times, right? With Felipe, the code on the right will actually produce the implementation on the left. Notice how the code does not express in any way how tensors are mapped onto ciphertexts. Now, think about how easy it is to change this whole code to work with 5 by 5 matrices. Okay, so which tensor operations does Felipe support exactly? Here's a list. Felipe supports element-wise tensor adds and multiplies, cyclic and non-cyclic rotations of tensor elements along a dimension, extending and shrinking tensors, striding tensors, dropping and inserting dimensions, reordering dimensions or transposing, summing all elements along a dimension, and replicating a tensor multiple times along a dimension. So much better, much more expressive than what FHE itself gives us, no? In order to support a high-level tensor interface, Felipe must reason about how tensors are laid out into ciphertext vectors on its own. This is done using Felipe layouts. We define layouts in Felipe as a permutation of the index bits of the tensor. So what does that mean? So here's a 4 by 4 matrix with 2 dimensions, I and j. And this is the tensor laid out in row major order in a 16-element ciphertext. The layout string for a row major layout is I1, I0, J1, J0. To understand Felipe layouts, let's see them in action. A matrix transpose in Felipe can be done through the reorder tensor op. Here it is applied to the tensor, and on the corresponding ciphertext, a transpose is just a change of layouts. So notice how the I and J layout bits are swapped, and the underlying ciphertext remains unchanged. Here's how shrinking looks like on the matrix, and here it is on the corresponding ciphertext. This, again, requires 0 FHE operations. The bit I1 becomes G, which is just a notation for a gap bit, which tells us that the ciphertext does not have all of its slots filled with valid data. And here's a stride applied to the tensor and applied to the ciphertext. Again, this requires no FHE operations, just a gap bit in place of J0. Notice that the old J1 becomes the new J0 because the J index only has two possible values. So we saw Felipe layouts in action. This showed us the first good thing about them. They make many tensor operations very cheap or free in FHE. Another big benefit of Felipe layouts is that they encourage what we call compaction. Let's see what that means. So, to set the stage, imagine a 4x4x4 tensor in 16-element ciphertexts. Because the tensor has more elements than can fit in one ciphertext, we will have to use multiple ciphertexts to store the tensor. Here's how data is laid out onto 4 ciphertexts, assuming a row major layout. We distinguish between slot selecting and ciphertext selecting bits. The ciphertext selecting bits specify which ciphertext the tensor index maps to, while slot selecting bits specify which slot within a ciphertext the tensor index maps to. Now let's say we have the tensor and layout from the previous slide, and then we stride along the x and y dimensions. Here's how that looks like in the tensor and in the ciphertext. Notice how the layout here has gaps and the ciphertext is not fully packed with valid data. So, we should try to merge these values into as little ciphertext as possible. And this is what we call compaction. So with Felipe layouts, compaction is relatively inexpensive, just 3 rotations and adds in this case. Now, any subsequent ciphertext adds or multiplies will require 4 times less FHE operations. In layout language speak, more generally, compaction means removing slot selecting gap bits with ciphertext selecting bits. So we see here how Z1 and Z0 took the place of the 2 gap bits induced by the striding. Like strides in this example, many tensor operations introduce gaps in layouts, limiting utilization. Cheap compaction is critical to actually using all the slots in the ciphertext, and Felipe layouts make this easy. Before Felipe, bootstraps were added manually to programs. This is tedious because it requires careful analysis to find narrow points in the program circuit. And critically, changing a small part of a program requires placing bootstraps from scratch. This totally kills composability. We invented a new algorithm which automatically places bootstraps as well as, or better, than state-of-the-art manual implementations. Please see the paper for details. Felipe is implemented in 20,000 lines of Python and C++ code and supports both CPUs and our Crater Lake accelerator. We evaluate Felipe on both CPUs and Crater Lake. The benchmarks include 4 complex workloads with state-of-the-art manual baselines, as well as 3 tensor kernels. Felipe matches or widely outperforms manual baselines that have taken many months to develop. Felipe is also 322 times faster than the prior state-of-the-art compiler, Chet+. We also see great performance for new programs. We quantify these results in what operational throughput they achieve. So we see here hundreds of millions of arithmetic operations per second. In summary, Felipe exposes a general, expressive tensor interface and solves the key issue of FHE composability. Local changes stay local. All of this while exceeding or matching the performance of manual implementations. In conclusion, for widespread adoption of FHE, we need people that are not FHE experts to be able to use it. Also, accelerators must efficiently support all FHE programs. We've seen how we have designed an accelerator that achieves this. F1 and Crater Lake deliver 3 to 4 orders of magnitude of performance improvement and enable new applications for FHE, such as real-time inference using deep neural networks like ResNet or LSTM. Bitpacker is an improvement to the state-of-the-art FHE implementation to deliver speedups both to CPUs and state-of-the-art accelerators. Felipe makes FHE programming accessible to non-experts. And finally, NoCap accelerates verifiable computation by 50x over a scaled-up state-of-the-art ASIC.